Okay, welcome to Cooking with Log. Today we are just gonna kind of quantify everything that we've talked about the past 2 days, all of those relationships between pressure and volume and temperature when it comes into the context of just dealing with gases. I thought I would first start out by talking about how pressure and volume are related when we're holding temperature and the amount of gas the same. So we're really just isolating the two variables, pressure and volume. I feel like I should give credit where credit's due. The person we can kind of thank for this is Robert Boyle. The pressure volume relationship is called Boyle's Law. Um, yeah, hey, Robert Boyle. Um, Robert Boyle's law kind of states that if we hold temp constant, when we multiply the pressure and the volume of a gas together, it gives us a constant. Okay, so what? Let's talk about what actually that means. If you picture making a container smaller, the molecules get closer together, and if they are closer together and they're moving at the same speed, they have the same kinetic energy, they're gonna run into each other a lot more. So that's pressure. So this relationship is the one example when dealing with gases of an inverse relationship. And what I mean by that is one variable is doing something different than the other. So the volume's decreasing, pressure's increasing. If we make the container bigger, the molecules get further apart, so they collide less. So when volume increases, pressure decreases. So Robert Boyle figured out that when you take those two variables and you multiply them together, when you do, if I get my pen ready, if you do pressure times the volume, that'll give us a constant. And so what's nice is we can actually set two scenarios equal to each other. So if we ended up changing the volume, you can figure out what the new pressure would be. So this is what we refer to as Boyle's Law. You don't need to know names at all, but if you are just isolating and looking at pressure and volume and how they're changing, this is the one equation you would do. P1 times V1 equals P2 times V2. P is pressure, V is volume, and they can be in any of the units that we've talked about. So you don't have to stress over this. So if I gave you like a word problem, you can go through and figure out, oh, here is mmHg, that's a unit of pressure. Here is a volume 430 liters, and now we're changing the pressure to 596 mmHg. So we can use Boyle's Law since this problem is just dealing with those two, and our initial pressure is 760 mmHg, and and the volume of that is 430 liters, and I'm changing the pressure to 596 mmHg. We can now solve for what the new volume would have to be for that to happen. And since it's inverse, if the pressure decreased, what would have to happen to the volume? Yeah, it would have to get bigger because they are doing opposite things. So I'm going to get 596 mmHg over here. We'll get that to go away. mmHg goes away, and the one unit we have left is liters, and I got 550 liters, keeping 2 sig figs. So that's what the new volume would be. Not bad, right? If you ever, I'm gonna skip that one. This, I've never been scuba diving. I don't know if we've talked about it, but I think I have a fear of like open water, so I don't know if I would be good. But your lungs are like a balloon, a really thin balloon. And if you picture, if you go down like 30 feet and you take a deep breath from your oxygen tank and you hold it and then you go to surface, the pressure starts to drop. And as the pressure starts to drop, the volume of your balloon gets bigger. And so you can run the risk of actually popping your own lungs. I just downloaded Rocket League, and so that's really exciting. See, I'm running up the stairs. That's how I get them to leave me alone. Shh. Okay. If we look at volume and temperature and how they relate to each other, we call this isolation, those two variables, when we're looking at just those two, we call that Charles' law. And he figured out that that they're directly proportional to each other. But this relationship only works if we're talking about the Kelvin temp. So this is usually where I see people make some mistakes, is keeping things in Celsius. But if we talk about, again, we're looking at something where the volume can change. So picture like a balloon. If I add heat, the particles move faster. And to keep the pressure the same, the number of collisions the same, the molecules would have to move further apart. So the volume would have to get bigger. So again, because both variables are doing the same thing, which is opposite of what was happening in Boyle's law, this is an example of a direct relationship. When temp increases, volume increases. And if you've ever bought like a birthday balloon in the middle of winter when it's cold outside and you walk outside, the balloon looks like it totally shrivels up. That's because as the temp decreases, the molecules slow down, and to keep the pressure the same, the volume gets smaller as well. It's a direct relationship. So because it's not inverse, if you take the volume and you divide it by the temperature, you get a constant. This is what we call Charles' law, and the idea is exactly the same. The biggest piece of advice, though, is remembering that this only is true if we are referring to the Kelvin temperature. So if we look at a problem, you go to Party City and you buy a balloon, and here's its volume, and it's filled with helium gas at 18 degrees Celsius, and then I walk outside in the summer and it gets warmer. Is the balloon going to get bigger or smaller? Bigger, because the molecules are moving faster. We can figure out what the new volume would be. We're going to use that equation, V1 over T1 equals V2 over T2. But in order to do this, again, temp has to be in Kelvin. So I'm going to write my initial volume as this. We need to figure out T1, 18 degrees Celsius plus 273 is 291 Kelvin. And now I'm changing the temperature to 38 degrees Celsius. 38 degrees Celsius plus 273 is 311 Kelvin. And we're just solving for V2. And we can keep it in milliliters. So once we get V2 by itself, multiply both sides by the 311 that's there. Kelvin cancels out. That guy is gone. The new volume that we have, I think with 3 sig figs, is 3,420 milliliters. It increased because the temperature got warmer than what it was. Magical. Next one. Let's look at temp and pressure. We call this Gay-Lussac's law. And this gentleman figured out that they are directly proportional as well. So just like Charles' law. Now, the one thing I do want to point out is we are keeping volume constant. So now we're not talking about a balloon anymore. We're talking about like a rigid container. And this is kind of the basis for all explosives. What we do is we take a rigid container, we put gas in it, and then as we add heat, the particles start to move faster. And if they can't spread out, they collide more and more, and eventually the pressure can become so great that it causes the container to blow up. So again, as temp increases, pressure increases. So this is a direct relationship because both variables are doing the same thing. This is also why, if you've looked at like your hairspray bottle, your shaving cream, or spray paint, they always have a label on the container that says don't store at temperatures above like 120 degrees Fahrenheit, because if it gets too hot, you can actually cause it to explode. And this is also the same thing that happens with your car tires. In the winter, when it gets really cold out, our tire pressure sensors go off because there's less collisions, the pressure decreases because it's cold. And then in the summer, when it gets hot out, the pressure increases. And so this is why usually in the summer, a lot of times you can suffer getting a popped tire if there's too much gas in your tire. Equation's the same, pressure over temp. And again, the same idea needs to be true. What, bud?
So when we were playing the game, I wanted to go to the garage, and then one started playing it, and now I'm not in the game.
Okay, tell her mom said to let you go to the garage and pick a new car. This is really professional. Here we go. Pressure, temp. Temp again has to be in Kelvin. We're going to use Gay-Lussac's law, this one, T1, P2 over T2. Our pressure is 3 atm. 25 degrees Celsius plus 273 is 298 Kelvin. And we are changing the temperature to 52 degrees Celsius, so T2. 52 plus 273 is 325 Kelvin, and we are just solving for P2. So multiply both sides by the 325, Kelvin goes away, we're left with ATM, and I got as our new pressure, since we added heat, the pressure should have gone up as 3.3 ATM. Oh my God, now they're screaming at each other upstairs. I don't know if you can hear it. So far, here we go. We learned this one. Boyle's Law. We know this one. And we know this one. There was one more person, last name combined. Conveniently, they combined the gas law. The gas laws. Whoops, that should be, dang it, that should be a 1. I'm just kidding, there was not a person named combined, but there's Boyle's Law. We can put them all over temperature, and that gives us what we call the combined, that should be a 2, the combined gas law. All together. Fun. Let's do one last problem. Here we go. I would look at a problem. I go, oh, I've got volume. Oh, I've got temp. Oh, ATM. Oh, that's pressure. I'm going to need an equation that has all three. We're going to use that combined gas law for it. And we simply are just going to plug the variables in. So 2.1 ATM times the volume, which is 25.4 liters, all over the temp is 298 Kelvin. And I'm going to run out of room because my handwriting is too big. V2 all over 273 Kelvin. And then you're just going to isolate V2, get V2 by itself. I do want to mention probably the world's most annoying law. One last one. This is called Avogadro's Law. Which, where have we heard him? Yep, he dealt with moles. This one drives me nuts. He figured out, or this law pretty much states that if you take a balloon and you put more gas in it, what happens to the volume? Yep, it gets bigger. So if you take moles, which they use the letter N to represent, if you add more gas, the volume also gets bigger, which is a direct relationship. So you can also use this law if you ever have a problem with volume and moles in it. If you try a couple of the sample problems, I don't tell you specifically which law to use. So I like you've seen me doing the problems, kind of underlining which variables are there and then figuring out which equation you're going to have to use. But that's kind of it. Those are our math relationships for our gases. We're going to learn one more in our last video and then pull some stoichiometry into it because I love it. That's what I need you to do. Okay, have a good day.